If everyone's ready, we'll begin. Today we will go over the complete setup of a neural network for the extended EMNIST dataset. Yes?
Where should we put the zip file?
Yes. So in the Slack channel, you'll see that I've dropped the zip file. And I'd like you to save it in, well, just in the same directory as the notebook. I just unzipped it in the same folder, so it's right there. And then within it, you see all that nonsense. Oops. Let's go back here. Right. So I've already posted the completed notebook, but I'm instead going to build it from scratch to give a better feel for how it progresses. But we will be following this broad overview of loading the data that we pulled in or that we've downloaded. Then we'll do some minor cleaning and preparation for input into the model. Then we'll define and compile the model. And after data and the model have been defined, we'll be able to train it. And then we can inspect its performance with Tensorboard. A visualization, I don't know what you would call it, a visualizer for the performance of neural networks as part of the TensorFlow library. And so this is all to get us familiar with the process of developing a neural network. And in the coming weeks, we'll refine aspects of it. In the following weeks, we'll talk about different model constructions, changing our use of layers from dense to convolutional and what that means, and transition into the handwritten digit project, which reminds me, I need to print out more of those sheets. I was going to say I'll pass them out, but I don't have any. So, to begin, we just want to, so like I said, first we're going to shape the data. First we'll load the data. And then we'll prepare the data.
Getting like 150 kilobytes per second, so
Ooh.
I got like an hour left on my download.
Is it that large? How large is it?
500 megabytes.
Yeah, it's not that big.
It's a half a gig.
Well, it's half a gig, yeah.
Do you have a thumb drive handy?
It might
feel
say
like I
2 minutes.
watched-
No wonder Git didn't like that.
Yeah, I think they want 50 meg or smaller. I don't know. Oh wait, just talking about it, up my speed to 3 megabits per second. So
Mine says 2 minutes left, and that was
Yeah.
about 4 minutes.
mine was 40 minutes for 3 minutes, and now 1 minute for 20 seconds.
I think you're supposed to average that over some
I think if you just talk about it,
reason. Make fun of it, so a little bit embarrassing.
Yeah.
Damn computers.
If you just bully it through.
I think mine has a funny 1 minute thing, 'cause just looking at the math, I'm halfway to 1 minute. We started this, I don't know,
I didn't mean to knock you off.
more than a minute ago.
I know you're good. I'm kind of trying something different by building what I've already completed as we go along.
Okay.
So,
Seems reasonable.
yeah, we'll see. I'm not sure. It may be easier for me. It would be easier for me just to point at the things I did, but I think it helps to do it step by step. And if I do it this way, then I'm forcing myself to go step by step and not skip anything.
Plus, we have to follow along.
Yep. So you should theoretically be able to copy and paste the things I'm doing into a new notebook that you're creating and get the same results. And if you don't find that to be the case, then holler at Matt or Dennis and we'll try to figure it out. So first, just the basic initialization stuff. So including importing gzip for unzipping files. Actually, we're not doing that here. I'm taking Matt provided a lot of the code needed to pull in the data. So yeah, total plagiarism, but thank you. We will be doing some visualizations, so we will need matplotlibs, PLT, then we need NumPy, of course. I don't remember what that's for. We will need to reference paths, and then we need to set seed for a random number generator.
The struct module is for actually unpacking the binary data from the EMNIST dataset.
Ah, yes. Let's see. Then we'll import the Keras things, so including loading model for if we have a previously existing one, a previously trained model, we can load in its weights, and we'll need the sequential layer model, or the sequential model and the dense layers. That'll be the primary parts of our model. We'll get to that in a bit. And in order to visualize, we turn off the screen. What's going on here? I've lost one sanity. All right, here we are. Hopefully that didn't corrupt my screen recording. So Tensorboard is used to visualize the performance of a given TensorFlow training session, and we'll be comparing it. I already ran it over a few different configurations, so we'll get to see that, hopefully. And then lastly, we'll need a backend for, possibly changing some of the configuration when it loads a data set. We may not need that for today. And then lastly, we'll need matplotlibs inline. If we evaluate that, it'll generate its images in the cell, on the Jupyter Notebook cell. And in some places, we'll be generating it outside. But if you put this here, it'll output display images in the notebook. So run all that nonsense. Ignore that. It's just saying I'm doing this inefficiently. Okay. So copying from the, copying from.
I really like your hashtag in your initialization document, just Keras things.
Yes, I was hoping someone appreciated that.
Noticed that.
So I've saved as a string my path for the folder. It's going to be pretty much the same for everyone except for your name, not mine. Unless you're on Windows, then in which case I actually don't know what happens there. So if you don't mind slacking that, if it's if someone needs help with that. Then I add the path for the folder where I saved all the images or the data set. I guess that belongs in there. So loading the data. Oh yeah, that's right. I need to keep this thing a little bit higher. Let's see if I can do that easily. Okay, can everyone see this line down here? All right, cool. I'll work from this angle then. So, speaking of angles. Yeah, this works much better. So, next, loading the data set, we'll start with this function here, which takes in a given file name, which in a minute we'll use the location of the zip file. It will, actually that's what I need a gzip for. Yeah, this is hard. Doing this, structuring this way.
What do you mean?
I'm simultaneously reading what I've already done and then rewriting it in front of you. So let's try that again. Because we'll use gzip here. And so yeah, Matt wrote this. It's to unpack the zip file. And this helps pull the data in so that we can, this is the first half of pulling it in so that we can then turn it into a NumPy array.
I extracted to a gzip folder.
That's fine. I also have it saved as a gzip folder, if you'll see that.
I believe.
Yes. So here is the notebook I'm working from, which I think you all were able to pull. So if you unzip it into the gzip folder, where if you unzip it, it creates a gzip folder with all the text and gz files, then that's great. That's perfect.
And if you have it somewhere else, it's no big deal. Just have to adjust the path that you used to move the files in.
Yeah, and we'll see that in a second.
Is that what you're using the OS library for?
That is to manipulate these paths
Okay.
and combine them.
What are you using the struct library for?
That actually unpacks the binary. So that these data files are in a specific format where they have a 4-byte quote magic number at the beginning, and then the dimensions of the data, and then after that is all the data, but it's all packed into a binary file. So the struct module is used there with these. If you look at these lines, there's like a greater than HBB, greater than I. Those tell it how to read the data in, which an explanation of that isn't particularly relevant to the data science, but if you want to know what that's doing, I can tell you afterwards or something.
Yeah, that's fine. I was just curious.
Right, and the way you would handle pulling in different data sets from online is different every time. So I don't want to focus too much on this, but this is how we read in this data set.
Sure.
Yeah, good question. So next,
And if anybody does want the details of that afterwards, I'll be happy to explain.
yeah. Next, this is the actual function that calls the specific binary files that we'll use. So we'll save the zipped dataset includes these 4 files, which are the training and test images and labels, and we'll use that as our basis for training the models. So I just saved the name of the training images, labels, testing, the training and testing images and labels, their file paths as the download path where you saved your gzip files. So in my case, it's under all this. Then inside that, the gzip folder, and then I call the name there. I did this so that anyone could replace their base project path, or so that you can define where you saved everything in the first line, and then everything else should work from there. Provided that you specify your download path wherever you save that folder as this here. Okay, so then I called those files into Matt's unzipping function. Then it saves them as NumPy arrays, and start with that. Takes a little bit. Actually, it did it instantly. That's interesting. Oh no, that's just a function. Okay, so then we actually load it. I'm going to call them raw files. Now, I think it may be different convention to save your data set using one name and then reusing it. I find that can be a bit difficult when you transform the data and then you want to go back and change something, but then you have to start over in order to do that. So I like to save things using weird names like raw. Okay, so we'll load the data sets, You can see the first one's loading in the training images. So it's an array of 28 by 20 images, and there are 697,000 of them. And these are the labels for those 700,000 odd images. Then there's another data set for testing. Same dimensions on the images, a different set of observations. Okay. So that's all we need for loading the data. Now to prep the data, we want to see that, as we'll see, as with many neural networks, you may want to have it in a specific format, and you may want to do some cleaning on it before you start to throw it in there. A couple different things include resizing. So for the dense model, it requires a single line. Supposedly, Keras is able to take a given NumPy array and flatten it so that it fits, but I wasn't able to get it first pass. I actually found out what I was doing wrong, but I'll stick to what I'm doing here. And another thing we need to do is to make sure that the values of the NumPy array are between 0 and 1. And I'll show you that it's not in a second by visualizing the data set. So let's see. It's already inline. Show. Don't judge my slow typing speed. If you use the color bar, it'll create a legend to it'll create a. Oh wow, that is not a. There you go. All right, yeah. So I took the 55th or the 56th or 55th element in the data set and just rendered it using the grayscale. And I also put in the color bar so that we can see the range of values that these pixels take. If they're completely black, then the data value is a 0, and up to 256 for white. So this is a 2, I think, or a Q. I'm not really sure.
Do you mind showing what it looks like without the transpose?
Yeah, so without a transpose,
Because for some reason the data is stored in an odd way, stored non-transposed. So that's what I think you have to do when you load it in.
right. So for those that didn't hear, the data is actually stored like this. It looks like a 4 or something like that. But all the data is flipped over. So we use the transpose to transpose it so that it's upright. Let's pick a different observation. That may not be helpful. That's obviously a 4, or an upside down H. But I'm betting it's a 4. See, if we didn't have the transpose, we just have, that looks like a 1. This is not helping my case.
It was really confusing when I was, well, that's a good example because it was really confusing to me when I was first putting this data in because I'd come up with things that didn't look like any kind of letter or number, and that's how I finally figured out they were transposed. If you flip them and then rotate them 90 degrees, they look perfect.
Yeah.
So like that looks like a minus maybe, but not a number. That looks like it could be a 1.
You know what? There's just no hope that this thing's going to train because I can't tell what any of these are. Oh, that works. I think that's a 4.
And it makes sense when you transpose it. That's the point I was trying to get across. The way the data is stored, if you're just trying to look at the images, it's going to be really confusing because your brain will not know how to process them unless you have much better spatial skills than I do.
Right. And hopefully my pace is going, I'm going at a decent pace to where you can follow along, type the same things, and evaluate them. Otherwise, I don't know. Okay, so Matt has also provided another way to visualize a bunch of data, a bunch of these bunch of these data sets. Let's see if this works. There you go. Oh yeah, that's cool because I changed that. Commented. Right, so I have it render it in screen, and it's putting it here. Where did you go? Well, if you run this chunk on your, oh, never mind. Oh, it must have stopped it. Here you go.
It's because you don't have the label.
Have I not?
That array of label layers and numbers. Not
Oh
inside
yeah,
the
yeah,
data.
yeah. You're right. I moved that around.
That's what you get for moving things.
Oops. So let's do that here then. Oof. Okay, so with the labels defined, I should be able to do this. Yes. Except it's doing it down here. Right, so Matt wrote this to scroll through, and then it shows different values as it scrolls through the data set at, I think it's random. Or no, it's over a,
It's just doing an order.
yeah, it's just visualizing them in order. This gives you an idea. Very cool. Okay, so now we're going to prepare the data so that it can fit into the neural network that we define in the future. Okay, cool. So right, so just to give you an idea, the shapes of each of the, I don't know if it was clear earlier, but the shapes of each of the downloads are as follows. So all the X's are the actual images, training and testing, and then the Y's are the labels that come with them. And like I said, the sequential model wants the images or the data set to be flat. So I need to know the total number of pixels within an image. So if it's 28 by 28, then I can multiply them together to get their 784. So print input shape and get the 784. Or rather, to show each of these the image height. I think y'all believe me, but here we go anyway. Yeah, so the images are 28 by 28, and I saved the full length of each image if they were flattened as 784. Okay, so to reshape them into a flattened image, and this is what I'm talking about saving. I'll save the new data set as, or after the transformation, I'll save it as a new set. So I'll save the train data as the original, but I'm going to reshape it using NumPy's reshape. And what that'll do is just change the shape of the NumPy array. And I want it to be whatever the, so I keep the, so the current shape of the data set is 70,000 deep, 28 wide, and 28 tall. And I want it to be same depth, but I want it to be 784 wide. So basically, I'll take each of those images and turn it into a string, and then each of those images will then be stacked on top of each other. So we'll still have the same depth, but a stringed image.
Does everybody get what we're doing with the image data?
Yeah, and always feel free to pause me and ask questions, because I may not be entirely clear what I'm doing. Yeah.
All right, say this is your image. It's 28 by 28. And I'm not going to bother to try and draw 28 lines here, but basically we're taking this first line, and this is just going to be, since this is 2D currently, it needs to be one-dimensional. And take this first line, and it's going to be a new array, NumPy array, and the second line gets stuck on the end, and then the third line, fourth line, so on. So it goes from a two-dimensional to a single one-dimensional that just goes across.
Right. Now, in order to get it to the first argument is going to be the depth, which is still the 70,000. And in order to get that, I'm just going to call the length of the array. And then for the second, I've already saved it as input shape. Then we should see that the dimensions of train X should be transformed. All right, so now we have the stack of images, stack of 1D images. We'll do the same thing for the testing set. Okay. So, like I said earlier, that the images or the data set, the NumPy arrays, the range of values go from 0 to 250. We can use it as is, but most machine learning models are safe to use if you have your values ranging from 0 to 1. So we want to normalize these values to be within those ranges. Now, because we know that the values take on the data takes on values between 0 and 256, we can easily get that by just dividing every value by 256 or 255, because it goes from 0 to 255, not 1 to 256. So first, to make things consistent on each data set, we're going to put it into a predefined format. Do that here as well. Oops. Test X. Test X this time. 32. Because the data as it comes in is an integer, we want it to be a float, so that when we divide it by another integer, we still retain precision, or the same precision between each of each of the observations. So say, so the data type is an integer here, but I want to turn it into a float. Then I'll show that it has changed to such. That takes a little while. Okay, so they're all floats now, which means they have decimals with 32-bit precision. Hope I'm saying that right. Okay, so like I said, we just want to normalize them by putting them all into values between 1 0 and 1. So I'll divide every value by 255. If you're not familiar with this, we're just saying that this is now divided by 255 and set it equal to that, which is the same thing as saying 255. I'm not going to run that because then I'll be dividing by 255 twice. But those are the same thing. We'll do that for this test set. Oops. After it's done that, we can see that the, oops, no, I forgot to change it. I don't want to print the raw, I want to do the new train set. And it didn't like that. I'm doing something different.
Did you say new train set?
Huh?
Like Lionel?
Oh, I already flattened the image. That's why. So it's not going to print it if it's.
Everybody else would.
Huh?
You could
Sorry, what was your question?
A reshape on the image right there in the intro.
Yeah, I could. So let's do the reshape. Let's see if I can do it in one shot. So then it's going to be length of train X, and then we'll make that 28 by 28, please. Array of size 2. Oh, yeah, that's right. So then I want to call that the 100th image of that, of all of this here. Had the order of operations wrong, and hopefully that works. Yes. Okay. So now we can see that this image has its values running from 0 to 1. There's a decimal there that you can't see, but that is a 1, trust me. Okay, so now we've got our training sets, or testing and training data into the proper format. Actually, the only thing I needed to do that for the training, but that's fine. So now we want to also change the format of the labels. We see that the labels come in the form of that the labels are actually just a set of numbers, and these are the values that they can take on. These are 62 different characters, so the labels will actually, I can just print them. So let's say print, what do we call them? Train Y? Oops, no, what did we call them? We called them, yeah, because I did not change them. Right, so you can see that there are just these numbers here, and these numbers are the different values within this string here. So the 0th element, the 0th label is a 0, all the way up to the 62nd or the 61st is a Z. So we'll use that to map. We'll use that to visualize when we plot the data set against their label, we can use this to say precisely what it is.
You could print out the label for that image you just showed as an example.
Print out the label for yeah.
Forward.
So if I did raw train y, and I called the 100th element, so whatever that is. Oops. Yeah, it says it's a 4 because it's also 4, but what I meant to show you was please don't be a number. No, still a number. Still a number. Someone give me a more magical number. There you go.
3.
Dennis, no. So yeah, it'll say that that is a 32. Well, it's the 32nd item in this string. So instead I'll say, I want the 32nd one. W. Cool. Hopefully you believe me. Now, do I need that? I don't need that. I will want to save the number of labels for when we just to keep that number at hand for when we're defining our model. You could just know that it's 62 and put it in place where you need to, but I prefer to have constants saved. Completely up to you. Let's see. All right, so now in order to put the label values into in order to train the model against these labels, we need for them to be one hot encoded, so that as we showed before in our neural networks, that if we have our inputs and they go through the model. In the last couple of weeks, we showed that if you ran your model, when it spits it out, this is its guess onto what the labels are, or what value it is. In this case, this would be a 0 all the way through a z, y, x, etc. When it guesses each of these, it wants to get to this, but this itself has to be encoded. The way that's encoded at the end of the model is it says that okay, it's going to be if it's this one, then it's 1, 0, 0. Well, more likely it's going to be some range of percentiles, but we round at the end to say that okay, it's actually the first element. Or if it's the third being at number 2, you'll put a 1 here instead. Or if it's the last one, it'll put a 1 there. So we need to get the labels in that format. And the way to do so is with one hot encoding. Luckily, we don't have to deal with that math. Keras already defines a function to take care of that for us. As such. Okay, so transforming the raw training labels using Keras's I can't type and talk at the same time. Two categorical method.
And for reference, this is the exact same thing we did with the irises.
Yes. Whereas the iris data set would say 0, 1, or 2 for the labels. We turn it into a length 3 label of zeros and ones to indicate which one it belongs to. We'll do the same thing here.
This one just becomes 62 long instead of 3 long.
I don't want to type that all that again, so I'm just going to copy paste. Hopefully, I know how to type. Please. Cool. So then I'll just print off an example. Oh. Yeah, so we've turned that into Right. So the fifth label in the raw label set is a 38, but if we switch to one hot encoding, it is a 62 length array, but the 35th element is turned into a 1, which is handy for training against in the neural networks. Okay. So now we've got all the. So now we're at the point where we've cleaned up all the input data, and one hot encoded our labels. So now we can start constructing the model. And all this may not seem like it makes sense, like why we would do this in that order, but this is typically the flow of things. You can jump straight to the model, but if you try to fit things in, you'll come across the issues of reshaping and with normalizing the values and one hot encoding. So then you go back and do that, and then it would make sense for you to put it above hand in the flow flow of things. So, ready to define and compile the model. Oh God, stop that. Okay, so I'm just going to take basically what Matt did in the previous class and define a model, define a sequential model, and I'll just keep adding these dense layers of different node sizes, and then the final layer with the number of categories, and its and different activation functions. Now, the key thing to note here is that the input dimensions, what goes into the model, is of the input shape, which we defined as before, if y'all recall. Print, input, shape. It is 784, the length of the image as a string, or as a one-dimensional vector. And Keras knows to look at the data set that is 70,000 by 784 and put each of these 70,000 in one at a time to train on. So we just need to define the shape of each observation. So we've got that. Pretty straightforward to compile. And that's all there is to defining the model. That is pretty straightforward for the sequential model. You can have more complicated, more nuanced or more sophisticated models. We'll get to that in future classes, but this is really just how you would do a basic one. And this is the same model type as Matt provided last week for the iris, a series of dense layers. And we'll talk about the different kinds of layers in future meetups. But for now, we just want to get it running, and then we can refine. So now we've got to compile the model by using the compile method. Pretty straightforward. We've got to define the loss function. So because we're dealing with a categorical class, we're dealing with categories on the labels. They are just it's either this number, this letter, this number, this letter. The discrete values we'll use categorical. So for our loss function, we'll use categorical cross entropy because that may make sense. Yeah, I don't want to speak to that too much. The optimizer, yeah, if you want to say.
Just a quick comment. It makes sense here for the same reason it did in the iris project, because the output that you want is a category. You want it to be a 0, 1, or 2, or in this case a 0 through 62.
Right, we're not dealing with continuous values to predict. And a popular optimizer is the atom optimizer. And we're wanting to train on accuracy. Positional argument. What did I miss? That. Huh?
assigning metrics. It's just,
Oh, yes. Okay, so we've compiled the model now, and now we're on to training. Oh god. Okay, to fit your model, use the fit method. I'm so glad they named these things appropriately. First position is the data set you're trying to train on, the actual data, and then you supply its labels. Then you'll define the number of epochs. And I'll get into what the epochs and batch sizes are in a second. I'll say that it's going to be one epoch in a batch size of 10,000. And that'll be it. So the epochs are the number of times that the model will pass all pass the data set through and back in. How many times it will go through that process of taking the model in, evaluating the weights, taking the model in, applying its transformations to get the guess at the end, looking at the loss, how inaccurate it was, then adjusting its weights in light of the loss function by using back propagation, and then starting over. And just keep doing that over and over again. So with one epoch, this is basically saying however the weights initialized in the beginning, that's pretty much how it's going to end. It's just going to spit out, this is what it looks like without back propagation. And then the batch size tells you how many images you're going to put in through the network at once. This helps define, the batch size is a number that you want to use depending on the capacity of your computer. Say I was working on a Mac Air that's really small. I don't want to use an extremely large value, as it will take a long time or will max out memory. Hopefully not. We're dealing with some pretty basic data sets, but you can adjust the size of the amount of data you're putting in through the network at once through the batch size. There's a trade-off. If you use lower values, you will be able to use up less space in memory at a given time, but your model will be very sensitive to with each pass through the network. So you will be while you will be able to save space on memory, you will be losing persistence. There's a better word for this, but it will be very sensitive to each pass through, and it will start to listen to whatever you gave it latest and forget what it's had earlier. So a larger value will retain that better, but then it'll be slower to go. It'll take up more memory to go through the network. Yes?
So batch one would grab one of those vectors that are the image, one at a time, adjust.
Yep.
So each time you feed it, it tweaks it, instead of requiring a batch, grab a whole bunch of them, and then adjusting?
Yes, I think we're saying the same thing.
Yeah. So batch size, the greater it is, the more accurate, would you say?
Not necessarily accurate, but less prone to yeah, there you go.
Trading off your time too. You can, if you have it do one at a time, it'll just take longer. You may not gain anything. You're balancing time, horsepower, machine, all good.
Right. So this should be rather quick, as I only have one epoch running that, epoch 1 of 1. And you can see it jumping by each batch size.
Yeah, it's pretty good. 18 seconds too.
Man, I am running way too many things on my computer at once. I already trained this, running over 50 epochs at a low batch size of 100, and it did not take 40 seconds to train, but I'm also running way too many things trying to display this. So yeah, I think this is the exciting part, because when you see this, you know it's working, or at least it's not going to break yet.
Or it hasn't broken.
Well, it's not going to break in one way. It'll probably break in some other. Okay, so it trained. We did it. Now let's see how well it did. I said inspect with Tensorboard, but we'll get to that in a second. I just want to add basic pass. Oh my god. Okay, so we'll print. What happened here? Oh yeah. So you can evaluate your model. So after you've trained it on the the training data, we can test it against the testing data by using the evaluate function. I feel like I'm going to keep doing this all night. So yeah, we'll evaluate it using the evaluate function on the testing data set and with the labels attached. Okay, so it's running the test data through the model as we've trained it, and then from that we can see its performance. Cool. So I want to print the first position of the results vector is just the loss, and then the second value is the accuracy. All right, so it's 33% accurate with a loss of 274%. I don't know how that's possible. That math doesn't make so much sense to me. But we know we want a lower loss and a higher accuracy. So we want to up those two numbers. So one of the ways we can do so is to train with a different configuration here. So let's try for 3 epochs. My God, that might take a while on this rather puny computer. But that's okay. I can talk about other things while we're waiting for that. So. Pop quiz. Can you run 2 cells at once? No. Oh man.
What was your best accuracy on what you did?
I think I got somewhere in the 80s last model I checked.
I'm going here with batch size of 200, and on my 11th epoch I'm at 72.5%. So it may reach 80 by 50 epochs.
Now is it showing loss is this?
Put my loss down 90%.
So I think this is 220%, whereas this is 45% accuracy.
Yeah.
So you're saying that you got a 0.9 something?
Yeah, right now it's 0.899 in the loss, and my accuracy is at just under 73% now. But on epoch 13.
Right. So we're at a point where you can play with your model and try to get better conditions to get a better loss and accuracy. Dennis has found his to be at a loss of 90% with an accuracy of what?
I'm creeping up. I might make 74.
With about a 74% accuracy. Which is pretty good for a simple sequential dense network. But as we'll find next time, there are ways to get even better with that. But as soon as it finishes, sweet, finished. Now we run this again. I want to copy paste that. All right, run it again. All right, so we've by increasing the number of epochs to 3, I have upped the accuracy to 65% and decreased the loss to 123%. So this sounds like if we keep going in that direction, add more epochs, we will get towards a greater accuracy and a lowered loss. We could probably add 10,000 epochs if we wanted, but as we'll see, that'll cause issues because we'll be overfitting. We will train the model to recognize the data so well that if you show it any of the values that you train on, it'll know exactly what it is, or very likely know what it is. But this has a problem when you're trying to show it anything besides that data set. It will probably not know what to do with it, or it'll inaccurately judge what it is. So that's something we have to fine tune, defining what's the appropriate amount of training for a given data set. And we'll be getting into that in the weeks to come. We've got about 15 minutes left, or about 10 minutes left. What I want to show you now, though, is how this performed on different number of epochs and batch sizes. I actually ran this morning using this handy dandy function here. I just ran a for loop over epochs of 1, 10, 20, and 50 at different batch sizes, so that I could see how it does to get just. I ran it over these configurations, and I want to see how it does over those. So I'm not going to run that here because that was already done. But oh yeah, and one thing before I get into that. We can display its progress using this function. What did I run? Yes. Okay, so it's saying that after that last run, it's saying these are its guesses for a few different things. It thinks this is an H. That may be true. I can't tell. It looks like an R to me. That's a 2. That's a 9. That's an 8. It's a T. It's actually doing pretty well. I wonder if I can do this on a different. I don't want to show it working. I actually want to show that it's not that great, but it's working against me here. That's an 8. That's a 4. That's a D. That's a 0. That's an 8. Q 4. Okay. Finally, it got one wrong. It thinks this H is an I or an L. I can't tell what that is. Yes, so it's not able to get everything right, but it's doing pretty well. As we saw, it's 65% accurate, and over 20 different values, it got more than that. So I'm just very bad at picking random numbers. So this is already in the notebook. You can play around with that to see different guesses that it makes. But now I want to show you the results of the testing using TensorFlow. TensorFlow's Tensorboard. Let's see if I can make a new one, make it a little bit bigger, not smaller. All right, CD, TDS, Python, CD lecture materials. I forget the name, so I have to do this every time. CD 15. All right, so I saved. Oh yeah, to show you how to do this, I saved. I defined this before running the model. I defined what's called a callback. In TensorFlow, or in Keras at least, you can define a callback, which is a method of saving a model's progress in terms of during its training. So that looks like this. You specify where you wanted to save. Did I save that? Yes. So I want to save this all in my project folder under a new folder called logs. Then I'll call Tensorboard with that directory, and I don't want it to plot any histograms, so I'll just say histogram frequency is 0. Then I want to write its, oops, oh my god. Huh?
Line 1 of that section is the project path. Path of the B instead of the B.
What?
And the square that you're in.
Yes.
on line
Yes.
1,
That is, I was just testing you. That was my favorite phrase to use when I was tutoring.
You can follow it up with a little star sticker or something.
I should have. I just call them good students. And they are. So, we save this as such. And that will save. So that will, so we've defined a Tensorboard variable that we can call when we run the model or train the model. And that in order to call it, we just do callbacks is equal to the callbacks list. Okay, so when it trains, it will add a new file into the logs folder that represents the performance of the model in terms of the validation, and the default is to save the accuracy and the loss. So when I train that, it will save it as a set of logs. I'm not going to do that because I've already done so. And I'll show you here. Oh my god. Thank you for coming to my TED Talk. Okay. Right, so I saved all the logs this morning when I ran it, or this afternoon, at these different, with these configurations. And in order to run it, we just do cd logs, we move in there, and I already forgot the Tensorboard. Oh yeah, that's right. Tensorboard, and we say log path is equal to, then we need the path for the logs. I'm going to save as path name, or copy as path name. Do that. Oh yeah. Gotta have the right environment. Try that again. Please work. Let's see. Log direction must be in database.
You need to put quotes around your.
Well then. Okay. How's everyone doing? So that's what I want. It'll bring up a
Just take that one.
right. So that's how you do it with an example. Transport logdir. I misspelled logdir. Did he quote it? And let's do it. Please. All right, so it doesn't like that I didn't specify A log dir must be specified when dB is not specified. How do I specify dB or get around that? All right, this is real-time Stack Overflowing things. I don't see Stack Overflow. We're doomed. Can't run Tensorboard after Bizel. No.
It's the last
Yeah, down there at the bottom. Yeah.
Okay, let's see what that one does. It's my favorite site. Okay. I don't think that's our error. Whoa. Can anyone read Mandarin? Oh, wow.
Just duck soup.
So there was no response to that, but I know we're not in the Wild West here, so it's just a matter of finding it. Well, let's see what this is. And at this point, you guys can play around with the different configurations on the neural net. I'm trying to get this to visualize the performance on the different models that are trained. So that's about as far as we'll go until I can find this.
Okay. When you get it working, you're gonna
Oh my God!
put your latest notebook up there? Or the-
It's actually already complete.
Except for the added notes that you put in. You did some variations from the notebook, because I was trying to follow along. I just tried to keep up with you, you scrolled by too fast.
Oof! I thought I was going slow. Okay.
Well,
Yeah, I know there's one.
there's the looping thing at the end. When you went and rescaled your one image, I missed that, so if you go there, at least I'll just type.
Okay, sure. There's actually another change that I made, and I just need to push that.
Okay.
I just haven't pushed it yet.
I just tried it on my machine, it worked fine. So.
Sweet. I did this. Tensorboard, log dir.
Yeah, and the log there is dash dash.
Oh,
So you hit control A to go back to the beginning of the line.
ooh. Learn something new
Control
every
A,
day.
huh?
Control E to the end, control A to the beginning. There are also some forward and backward individual word keys there.
Ah, yes. That looks nice. Matt gets a gold star.
Yeah, we get through.
That's what he meant to say.
All right. So how do I open that? That should be at localhost 6006, please. I'm excited. Wow, look at that. It's crazy.
Wow, it has broke all over.
That is pretty crazy. Oh yeah, that's right. Because these are different trains. Now the way it's plotting it is by step and not by total run. So you can see these short paths are actually just the these short paths are for the small epic sizes. I think you can kind of see it. This would be the let's see, does it specify? Yeah, the length 10 epic runs, length 20, length 50. I thought I had another value in between. Oh yeah, and these small ones are probably the ones. And Tensorboard does this weird thing where I'm not sure how to fix this, but it will attach the ends of each graph. So you see that straight line that jumps back? It's just going back to redraw the previous graph.
It's too lazy to pick up its pen, huh?
Yeah.
Awesome.
Yes. So here we go. So we found that the best model in terms of accuracy was, if I could click this up here. This model ran at 50 epics down here Let's see what else we got. Tensorboard will also let you see the graph, so how the operations are constructed. It's a lot of magic, but this is how it constructed the graph. All TensorFlow models have this, a graph that shows the flow of operations that happen at each step. This is useful if you knew what it meant. I don't.
I'm sure.
But if you read any papers online, you'll see them reference their model in the form of a graph. So you can, if you knew how to construct, if you knew the logic of the graph construction using TensorFlow, you can take it from other research papers. I haven't gotten to that point yet, but I'm pretty excited to try it. But what I'm really trying to get at is the most optimal configuration. So here we go. There we go. So it says the best. It didn't name it. That's weird. Huh? Well, okay. It says the best model that trained was named period. So I don't know which one it is. I'm not sure why it's not pointing at it, but it's some number of epochs with some batch size. But the best we could get out of all of the training, up to 50 epochs, up to 10,000 batch size, is just below 60% loss, and just up to 80%, just above 80% accuracy. And this is with a simple dense model. We could do this. We could train this even more over longer periods of time, and see how that performs on the test on the training data. But there are probably better ways to do it, and that's what we'll be covering next week by introducing the convolutional neural networks.